Hello there. In this video, we're going to talk about divisibility rules. I've always been interested in divisibility rules. This kind of ties into my previous video about mental math tricks and knowing things to make your computations easier. So what I've got here was a very clickbaity title that I'm going to go through all the divisibility rules of 0 to infinity. I will explain that. But I want to go over some key ones because there's a lot of similarities that end up coming from divisibility rules. So let's very quickly start with divisibility of 0. This is one that people always have a knee-jerk reaction to say, okay, what's a number times 0? So the number I'll be talking about in this video is 39,916,800. Is that number divisible by 0? And that is no, nothing is divisible by 0. I just wanted to use this opportunity to reinforce sometimes there's that knee-jerk reaction, oh, divide by 0, the answer is 0. No, nothing is divisible by 0. If you type it in your calculator, you will get an error, and that's because depending on what you're dividing and how you do the calculations and what functions you're looking at, you could get an infinity or a negative infinity, but that's another topic for another video. Now, what's divisible by 1? Everything is divisible by 1. It's almost not even worth mentioning because if you've ever done things like factor trees, you don't break it down into 1 and something else because that something else is just itself. 2. 2 is an easy one to remember. It's anything that ends in 2, 4, 6, 8, or 0. In other words, it is an even number. And we can tell my number here, 39,916,800, is even because it ends in 0. So this will be divisible by 2. And now let's go ahead and look at some of the easier ones, maybe not directly in order of my list, but another easy one that was often brought up is 5. These numbers end in 0 or 5. So once again, 39,916,800 is divisible by 5 because it ends in 0. Now, another thing, 10 would be one where it ends in 0. This is the famous computational trick that if you have an integer that you're multiplying by 10, you just add 0 at the end. All right, let's move on to 3. 3 is a famous one, not because it has an easily identifiable trick. It does require a little bit of work, but it's still a famous one. And that's if the sum of the digits is divisible by 3. So let's take a look at this number. Is it divisible by 3? Well, let's add 3 plus 9. Plus 9, plus 1, plus 6, plus 8, and then we don't need to add the 2 zeros. Well, I know 9 and 9 is 18. So 3 plus 18 plus 1 plus 6 plus 8. I know we get 21 here. We get 22 here. We get 28, and then we get 36. So yes, this is divisible by 3. And you can repeat this as many times. If I, for instance, didn't know that 36 was divisible by 3, then we can repeat it one more time. 3 plus 6 is 9, and then I know 9 is divisible by 3. So we're good. This number is divisible by 3. Next, let's take a look at 9. This is a similar situation if the sum of the digits is divisible by 9, divisible by 9. Now this is handy because we basically perform the check for 3 and 9 at the same time. And if we go back to our sum, 36 is divisible by 9. Like 3, we can also do it again as many times as we need, and we know 9 is divisible by 9. So that means our number is divisible by 9. So from there, we get into a little bit of murky territory. Let's go to 4 next. 4 has a rule that if the last two digits is divisible by 4. Now, I will say in this video, I won't be getting into any kind of proof that these are the rules. You're kind of just taking my word for it. If you would like to see a video regarding the proofs of these, leave a comment in the description. But this is kind of a tricky rule because it requires you to know the numbers of 4 that are divisible by 4, or the numbers that are divisible by 4, pardon me, up to 100. Now, the last two numbers of this are double 0, and 0 is divisible by 4. In fact, 0 is divisible by everything. That's different than saying everything is not divisible by 0. So this number is divisible by 4 because I know the last two digits, double 0, are divisible by 4. And that's to say that 0 divided by 4 is 0. And that leads us into the divisibility rule for 8. If the last 3 digits is divisible by 8. Now, pardon me, this leads us into, again, a little bit of murky territory, because if you don't familiarize yourself with all the 2-digit numbers that are divisible by 4, if you don't familiarize yourself with all 3-digit numbers that are divisible by 8, that would be up to 1,000, then you leave yourself in a bit of a precarious situation. Well, this is where, in one of my previous videos, I mentioned knowing long division is handy. Let's say the last 3 digits, I didn't know that was divisible by 800, or 8. That 800 is divisible by 8. I can perform long division and just see 8 goes into 8 one time. And I subtract my 8, drop the 0, and I can see these last 2 are going to be 0. So yes, I got no remainder. This number is divisible by 8. But you only need to perform that on the last 3 digits, and if it's for 4, you only need to perform it on the last 2 digits. So not a terrible amount of work to show here, but worth memorizing some numbers so you can make a split-second decision. From there, let's go into 11. 11 is one of my favorites. So what I'm going to do really quickly, I'm going to edit this. I'm going to go ahead and I'm going to erase this work so I have room for my divisibility rule by 11. Okay. So there you go. I went ahead and I cleaned it all up, and I even wrote out the divisibility rule for 11. This is one of my more favorite ones. This is an alternating sum or difference of digits. So what I do there is I'm going to start with the 3. Now, the fact that I'm starting off with a positive 3 means the next thing is I'm going to subtract 9. Now, this is where I say alternating. We've taken the difference. Now we're going to take the sum of the next digit, and then difference of 1, sum of 6, and then difference of 8. And order of operations, we've got to go in a left to right fashion. So I'm going to start here, and I get so the end result has to be either 0 or a multiple of 11. Now, 0 is a multiple of 11, but it's often forgotten that it is. So this number is divisible by 11. And again, like the sum of digits for 3 and 9, you can do this as many times as you want. It just so happens that this time I got a 0. So that's always the best case scenario, is when you get a 0 in these instances. All right, from there, I'm going to go from one prime number to the next. I'm going to go to 7. Now, when you research this, there's a couple rules you can do, and that is that we can take the last digit times 2 and then subtract from remaining digits. That's one rule, and that's the one I recommend because it involves subtracting. Or we can multiply by 5 and add. And I'll go ahead and show you both of those. Let me go ahead and get this cleaned up so I can show more work. All right, so let's start with the last digit times 2. So the last digit in this case is 0. So 39, 916, 9 916, 80 minus 2 times 0. Now that's not going to change my number at all. So that gives me 39, 9, 16, 80. And now this is where that rule of repeat it as many times as you can come handy. So if we do it one more time, we can see we're going to get 0, and we're just going to get 39, 9, 16, 8. So now we really get into it. So let's take that 8 and multiply by 2. So 39, 9, 16 plus 2 times 8. 2 times 8 is 16. And adding that to this, I will get 16 plus 16 is 32. So my digits now are 39, 9, 32. Well, let's do it one more time. Still no word yet. So 39, 9, 3 plus 2 times 2. And I just realized I'm supposed to subtract. So that's a computational error on my part. I apologize for that. So let's subtract. And this actually becomes double 0. In which case now I will be subtracting by 0. There we go. I went ahead and realized I was adding instead of subtracting. Now, right off the bat, we got double 0 now. So once again, if we repeat this process, we're going to be subtracting 0 each time. So we can drop the zeros. So we just go to 399. Now let's do this. Now we're really getting into small number territory. 39 minus 2 times 9. This is 18. So 39 minus 18, and now we get an answer 21. And 21 is divisible by 7, so that means this number is divisible by 7. Now, why do I recommend the subtraction strategy? Well, you can go through it. Instead of doing subtracting times 2, we would add 5 times that number. Well, as you can see, if we're adding, the number is going to keep growing and growing and growing, and we're not going to get to settle on a point where we're comfortable knowing, oh, this number is divisible by 7. If we subtract, the numbers get smaller and smaller and smaller, and then we have a number that we can definitively say, oh yeah, this is divisible by 7. Now, I get into this because I want to also bring up other primes. Now, 13 is an interesting one where we can subtract 9 times the last digit. So we go through this same process, or you can add 4 times the last digit. But again, in using the most optimal strategy, we subtract 9 times the last digit. And if you do your research on this, all prime numbers have this kind of algorithm. You just have to look up the prime number and what numbers pertain to it. So this is where my gimmicky let's go to infinity comes into play. I just covered all the prime numbers for you. Now we get into composite numbers. 6 is an easy one. We just need to determine if it is divisible by 2 and 3. And this is a trick of computation's divisibility rules using composite numbers. Is you find 2 numbers that are relatively prime, that is to say 2 numbers where their sum, or their greatest common divisor is 1, and we test those rules. So for 6, it's 2 and 3. This number is divisible by 2 because it ends in 0, and we did the calculations earlier that the sum of the digits is 36, so it's divisible by 3. So we kind of make a mental note that this number is also divisible by 6. We don't actually do a specific test for 6. We just do a test for 2. We do a test for 3. If one of them fails, then it's not divisible by 6. And this brings us to our last number on this list, 12. What would be 2 numbers that are factors of 12 that are relatively prime? Well, that would be divisible by, I chose 3 and 4. So this, again, number was divisible by 3, and we even did the test earlier for 4, so that means it's also divisible by 12. Now, if we went through, I wasn't going to do 13. You go through and do the test for 13, it's not divisible by 13. That's because this number was not chosen at random. This is 11 factorial. But wait a minute, if it's 11 factorial, how could it be divisible by 12? Because part of the factorial is that it multiplies by 3 and 4 automatically giving us a factor of 12. If you liked this video and want to see more with divisibility rules, leave a like. Otherwise, subscribe, comment below, and thank you for watching.